So, I mean the title and the summary of the talk are same, and it's basically the pseudo-random unitaries are neither real nor sparse nor noise-based. So this is a joint work with Tobias Hall, who is in the audience, and Dax Go, who is not in the audience. So this is a take-home message here. So a pseudo-random primitives, like whenever people talk about them, like they can be pseudo-random function, pseudo-random strings, or they can be pseudo-random unitary or state or any pseudo-random primitive. It's easy to prepare, but it's hard to distinguish against truly random objects. And why do we want pseudo-random objects, like the pseudo-random primitives? And this is because randomness is very costly. I mean, true randomness, I mean, is very costly. And that's why if you think about, let's say, in algorithms or in crypto or at many places, like people are interested in pseudo-random objects. And that's why, like in quantum case also, there was this question which was asked, like, can we have pseudo-random states and pseudo-random unitaries? And I will discuss what is pseudo-random states and also like pseudo-random unitaries. But constructing a pseudo-random unitary is an open problem, like still an open problem. And we don't solve this problem, but we prove that certain kind of families of unitaries, they cannot be pseudo-random unitaries. And moreover, we also introduce the notion of something called pseudo-resource. So the resource theorists might be interested. I mean, and that's what connects this talk to the resource theory conference, because pseudo-randomness is a resource, right? And so that's the summary and all. Next, like another take-home message which you should. So maybe I will continue talking. Okay. So there was this paper which came recently, computational entanglement theory. And like in resource theory, we don't care about efficiency. Like everything is free. Not everything is free, but I mean, like what people care about, like computational efficiency is not taken into consideration. So I mean, is LOCC really free? Like, can you have, local operations where the operations are, let's say, inefficient, or let's say the classical communication part, like whatever. And similarly, so I mean, there was this notion of pseudo entanglement which was proposed last year, and then building on that, Tomavidic, Friedman, and Brakowski, they came up with this notion of computational entanglement theory. And people in the audience, they might be interested in, can we, this question, like, can we have a computational resource theory, like, let's say, computational coherence theory. So it's basically the question of, bringing the ideas from computational complexity to the, to the land of resource theory. And not only caring about, let's say, I mean, looking at these notions also from the efficiency perspective. So why is cryptography, interesting? Because I mean, when we talk about pseudo-randomness and all, it's basically it's question about cryptography. And if you think about, when I have been interested in cryptography for basically for machine learning. Like if you think about crypto and machine learning, they are just opposite of each other. So like in crypto, we try to hide patterns. In machine learning, we try to find patterns. And there is this very nice, survey by Rivest, like it was there. And And in the survey, basically, Rives talks about, like how these two fields, which basically, let's say, cryptography and machine learning are just opposite of each other. So whenever there is a hardness result, machine learning people get sad, but then the crypto people get happy because that hardness can be used for providing security. And then if you think about black holes, like, why did here with crypto? Black holes are, like the ultimate one-way functions. Like you can go in, but you cannot come back. So, in fact, recently there was a paper by Zvika Brakeski which said that black hole ticket decoding is quantum cryptography. So using physical, like argument, like Zvika motivates, why there can be, like cryptography possible, let's say. So and then cryptography is useful for cryptography, and then on top of that, let's say even for finance and all, you can use crypto. So in crypto, like there is this question about what is the minimal assumption under which you can have crypto. So like, let's say there is this notion of one-time pad, but one-time pad is very costly. And that's why what people use is something called pseudo one-time pad. And for pseudo one-time pad, the string that we use is not really random. It's basically pseudo-random. And it's output of something called pseudo-random generator. Or like some pseudo-random function. But one could ask, like, what is the bare minimum that we require, starting from where we can do crypto? Now, the bare minimum that people talk is this thing called one-way function. And one-way function is something which is easy to compute but hard to involve. So a simple example you could think about is, let's say, multiplication. Like take two numbers, it's easy to multiply, but like hard to factor. And I take there is this definition which is basically like maths. In maths, what I said, taken from this Goldwasser and Villari notes. So one can ask, like, does one-way function exist? And if you can prove that one-way function exists, let's say mathematically, then you will get a lot of money because if there are one-way function, then P is not equal to N. So proving that one-way function exists is is an important question, but then based on physical arguments and so on, like let's say from thermodynamics, people try to motivate that, let's say it's easy to scramble an egg, but like difficult to unscramble it. And you can make it more rigorous, like, and that's where like that black hole thing came into picture. So recently there was this notion of pseudo-random quantum states was proposed by Lee, Ikai, basically JLS, G, Liu, and so on. And these states, they are efficiently computable states that look like hard random state. Now, when I say look like hard random state, it depends on who is looking at it. So it basically depends on there will be some adversary, or let's say some. So that's why if you see in the very beginning, I had this. There was this picture where there was a challenger and there was the adversary. And in crypto, you always have these two people. And then this challenger is putting a question to the adversary, and then adversary has to like tell whether it's let's say the truly random object or the pseudo random object. And an adversary can have some power. So let's say in the classical case, classical community assumes the adversary to be some BPP device. In the quantum case, like now we assume the adversary to be quantum polynomial time. So these hard pseudo-random quantum states, they are efficiently computable states, but they look like hard random states. So basically, to a quantum polynomial time adversary, given polynomial many copies of the state, they cannot distinguish between this state and hard random state. This is not a T design, we can discuss about that later, but it's like T designs are like information theoretic approximation of hard randomness. This is computational approximation. And more than that, like there was this very nice paper by Kishor Bharti where it was showed that they are, in fact, like there is a oracular separation between one-way function and pseudo-random states. So one-way function is the bare minimum to do cryptography. But then imagine a universe where BQP is equal to QMA. In that universe, one-way function may not, quantum secure one-way function cannot exist, but still pseudo-random states can exist. And that's very powerful because now, like we can have pseudo-random states without assuming one-way function, which was, the sacrosanct assumption in the classical world. So this is like, whole dependency and all. And yeah, I mean, so basically you can see that, like you have pseudo-random states sitting there, and this, and it was recently shown that it also implies private key. So pseudo-random quantum states are very useful, like you can do cryptography with them. There are commitment and signature schemes which people have proposed, starting with pseudo-random states. And very nice paper was there by Aronson, Gulag, and others, Vazirani, and so on, something called quantum pseudo-entanglement. So to motivate you, like if you look at these pseudo-random states, there are pseudo-random states such that if you take a like partition and calculate the von Neumann entropy, that goes like log n. On the other hand, if you take hard random states, and for that if you calculate, it can be it can scale like n. So there are states which have exponentially small entanglement, but mimic those hard random states which have which are highly entangled states. So in that sense, the question they were asking is that to what extent entanglement is a free level quantity? Can we feel entanglement? So in physics, what cannot be measured, is not physical. That's this is a very common argument that physicists talk about. But maybe we should think what cannot be measured efficiently is okay. I cannot call it unphysical, but it's not I don't know, one has to come up with the right word, but it's not in true sense physical or something, not polytime physical. So yeah, there was this most of pseudo entanglement, and then that's the question, like that maybe all of the so if you think about, let's say, the theory of the computational complexity theory, earlier people were interested in like what is computable and not computable, but then later they got interested in what is efficiently computable. And in physics, we are very much in the regime of what can be measured and what cannot be measured, but maybe we need to make transition to this question of what can be efficiently measured. And that's where things connect to resource theory. So also, like there was relation to ADS-CFT duality, wormhole paradox, and so on. I haven't read in detail, but here also they used pseudo-randomness to understand some of the. So this is from the JLS paper where they talked about, like there's in the classical world, we have uniform distribution, the quantum world with hard measure. Then there was T-wise independent random variable, the quantum analog of that is quantum T designs. And in classical world, we have something called pseudo-random generator, pseudo-random function, pseudo-random permutation, whatever. All of these objects, as I said in the beginning, they are basically easy to prepare, but they look like, they're truly random analog. And the quantum analog was missing. So in some sense, the computational approximation of true randomness in the quantum world was missing. And that's where pseudo-random state and pseudo-random unitaries came into picture. So pseudo-random states were proposed, and they proposed a few pseudo-random unitary construction, but they couldn't prove it.
10 minutes.
Done or
No, 10 minutes only.
So yeah. So constructing a pseudo-random unitary is an open problem. So basically, they had proposed some, candidates, and we ruled out those candidates, through our work. We do not propose new candidates, but we rule out, like a family of construction. On top of that, many of the construction which are there, so here, you can use basically saying that constructing a pseudo-random unitary is an open problem. Like this was the Simon Institute talk this year, colloquium, and that's what they were discussing, that it would be nice to have one. And people have been trying to build pseudo-random unitary, but so far there has been no success. So basically that's what we show, that it's not real, it's not sparse, it's not noise robust. And this noise robust part, in some sense, like a matter of worry, because in classical case there are strings, but in the quantum case, maybe you should think about like not pseudorandom state, but then city matrices or something, because pure states are like kind of a misnomer, right? So basically, if you add a small amount of, let's say, non-negligible noise, then in presence of that, the security of pseudorandom states breaks down. And all of the quantum cryptography starting from pseudorandom state, like in the quantum case, is done starting from pseudorandom state. So if the pseudorandom itself is not noise robust, then it implies that like whatever you you build on top of that, that's some that's some problem. And the whole idea, the key idea, I mean, I may not be able to cover the entire talk. Like last time I talked, I could cover up to motivation. This time at least I can. So it's basically the key idea is this called computational indistinguishability game, which you will see a lot in any crypto textbook. That's like Katz and Lindell or something. And the idea is that there is a challenger and there is an adversary, and the challenger has, let's say, will toss a coin and we'll have two options. So in one case, the challenger will prepare, let's say, the random object. In the other case, it will prepare the candidate pseudo-random object. And it will, let's say, it will be equal to 0, then it will send the, let's say, the truly random object, let's say the pseudo-random object to the adversary. And if it's 1, then it sends, like the truly random object. Now, this is where, like the connection with resource theory comes. So the adversary here can measure certain properties of the objects, like which they get. And all those properties which are efficiently measurable, let's say for the truly random object, on those properties, the pseudo-random analog must agree. Otherwise, the adversary can use like this, the value of this or like resource or object to differentiate between pseudo-random and random. So what are the different properties that one could think of? One could think of imaginarity, entanglement, non-stabilizerness, coherence, purity, whatever, and so on. And one can do like some kind of a property testing, and through that like one could try to distinguish between truly random and the candidate pseudo-random. So we have like these are the results. I mean, basically that they are pseudo-random states and unitaries are fragile to noise. And our findings imply that implementing pseudo-random states in unitary as well as related primitives in NISC and early fault tolerant systems is not feasible. Moreover, pseudo-random unitaries are neither real nor sparse, and some other results related to property test. So there is some property testing results. And then we also talk about the pseudo resource state ensembles, and so similar to pseudo entanglement, one could in general think about like pseudo resources, and in principle one can talk about like pseudo resource primitive ensemble. So you can think about pseudo resource density matrix ensemble or unitary ensemble or so on, with more general construction. So in one case, you have, let's say, basically the ensemble consists of two kinds of objects, such that like two family of objects, such that both of them are efficiently preparable, and one of them has Fn amount of resource, the other has Gn amount of resource, and no polytime quantum adversary can distinguish between them. And there was some resource gap that we talked about, related to various resources. So I cannot go through all these, but let's come to the lessons part. So there is some technicality and all. So the lesson is that QML can help focus attention on. So sometimes like by looking at the other question of, let's say, QML, you can answer things about crypto security. Noise must be taken into consideration. Fault tolerance is the way to go. Need to define noise over pseudo-random primitives. And then the adversary which I assumed was, like quantum polynomial time, but it need not be quantum polynomial time. Like we don't have quantum polynomial time adversary at the moment. So what if the adversary is in this device? And in fact, this complexity class has been defined, and maybe one can study that. What about like pseudo channels? Can we have random CPTP maps, pseudo random CPTP maps, and so on? And in general, like one could think about this way of doing quantum information currently is very much, like 1950 Shannon style. Like maybe we have to come to 1970 and do some kind of, like we have to bring efficiency into picture also. And there is a recent and related work where we talked about some of the motion on homogeneous spaces, which is like some kind of a generalization of quotient spaces. Yeah. So it's a generalization of that, and that's it. I think if you have any questions, please.
Thanks, Kishor. Thank you.
Hi, thanks for the talk. I guess I could ask a question about how you define pseudo-random unitary. Like I could define a black box that flips a coin and gives you one of two pre-programmed unitaries, and that could be called pseudo-random. But I guess that's not what you're talking about.
Yeah. So pseudo-random unitary, when we talk about, like, we have to talk about what is the gold standard here. So the gold standard in the quantum case, it's the random unitary which people talk about is Hall random unitary. So you will have oracular access to, let's say I'm adversary and you are the challenger. Sorry, I'm challenger. And so one of us like prepare prepare this black box and gives it to others. So I flip a coin. In one case, let's say I give you the black box which does implements like Hall random unitary. In the other case, the black box like implements the candidate pseudo-random unitary, and there should not exist any polynomial time computable property such that on that property these two cases disagree. Because if they disagree, then you will be able to tell apart that the construction which is there is not a pseudo-random construction. It's a pseudo-random unitary.
Okay, so you say it's pseudo-random if there is no algorithm that's polynomial in, say, number of trials or something that can discriminate.
Yeah. So the best way to do is to basically assume that, let's say, assume some pseudo-random function or whatever, and starting with this kind of assumption, you show that if, let's say, a candidate construction can be distinguished against Hall random unitary, then like the underlying assumption will fail, like the one-way function cannot exist, or or whatever. So you have to do some kind of a reduction, and that's how you prove that a candidate construction is a pseudo-random unitary construction. And so far nobody has done it.
Okay, thanks.
Okay, thanks, Kishor.